start.
You consider.
So first, review Young-Mills equation and instantons in dimension 4. So it was the generalization from the abelian gauge theory, where, for example, the Maxwell's theory, where the gauge group is U1, an abelian group, and Young and Mills, they considered gauge theory with non-abelian gauge groups, and particular SU2. And so we do it, we study the Young-Mills equations in dimension 4 with Euclidean metric. So there's a reason behind considering Euclidean metric. So if you want to actually compute path integrals, then for them to be well defined, you need to analytically continue. And this analytical continuation is precisely the time coordinate t goes to it, which is precisely we know as the weak rotation, and that will transform the Minkowski space into the Euclidean space. So although it's very customary to study this physics, specimen physics in Minkowski setup, but we need to study Young-Mills in Euclidean framework. And so let's review the gauge theory dimension 4 on R4. So I'll start with the gauge group SU2, and that's my generator, very well known. I'll consider the SU2 valued gauge potential A mu, which component wise you can write it this way, and then the associated field tensor F mu nu this way. So clearly the non-abelian part is reflected in that commutator bracket, and that's the gauge transformation. So now if you consider the gauge covariant derivative, then the Young-Mills field equation, you can write it as d mu f mu nu equals 0, and which you can clearly obtain from the action by using Euler-Lagrange and finding the critical values, and those are precisely you can derive that equation from that. And now if you consider the dual field tensor, which for the mathematicians is just the Hodge dual, then that will satisfy the Bianchi identity. It will always satisfy the Bianchi identity. So now a gauge potential A mu, I'll call it an instanton. If it satisfies this instanton equation, F mu nu equals plus minus half epsilon alpha beta, F alpha beta. And of course, one will be called the anti-self dual instanton, other will be called self dual instanton, depending on what kind of convention you put on epsilon. Either plus or minus will give you the anti-self dual instanton. And of course, from the Bianchi identity, it's very clear that the instantons will satisfy the Young-Mills equation. So now let's do it a bit more mathematically rigorously, and which will enable you to do this on any 4-dimensional manifold rather than just 4, and more coordinate slash index free notation. So I'll start with a compact oriented Riemannian 4 manifold, and we'll consider a compact gauge group and a principal bundle P on my 4 manifold. Now I can always consider the adjoint vector bundle. So for P, the principal bundle, I have fiber Lie group Z, and so you consider the Lie algebra and have a vector bundle where your fiber is precisely that Lie algebra. Well, and you know the Lie algebra is the adjoint representation of the Lie group, and that's where the name adjoint vector bundle comes from. And the curvature will be a bundle valued 2 form. And then the Young-Mills functional, I can write it as this integral x f squared. It was exactly the same as the action I wrote it before, but in a bit differently. So this is the same thing as integral of FA with star FA.
So which bundle are you thinking the connection living on? Is it the principal bundle?
Well,
or does it not matter? Sorry, I should know this.
well, technically it doesn't matter because one will determine the other, but for simplicity, you can always take it on the vector bundle. And in fact, you can write everything in principal bundle language or in vector bundle language. So, as I mentioned, Young-Mills connection are the critical points of this function, and you use the Euler-Lagrange equation to find these critical points, and you will precisely get the condition, this condition, which is which we know to be the Young-Mills equation. This codifferential is minus star differential star. And then the instanton equation can be written as star FA equals plus minus FA, where the plus will call it the self-dual instanton and minus will call the connection the anti-self-dual. And using the second chart class, you can actually prove that these instantons are the minimum of the Young-Mills function. Now let's move on to instantons in higher dimensions. So the first obvious question is why higher dimensions? And the answer shouldn't surprise you. It's string theory and supergravity. So I wrote down a lot of history. Maybe I'll go through them because even I didn't know about this development completely a couple of weeks ago. And I did a lot of literature review, and it's helpful to look up those papers and gradually see why, and how we are here. So the string theory revolution started with the study of S matrix by Heisenberg, and a new era in 1974 started when oh, nice. Oh, looks like it's the whenever I laser.
You'll have to be no pointer. So you can use the
Oh,
mouse.
I have this.
Yeah.
Nice thing.
But you can use the mouse if you want.
Right. When these two people started the study of the bosonic string theory, and that eventually led to the idea of supersymmetry, and it became popular. And to do this properly, they needed to bring back an old theory called Kaluza-Klein theory, which was mainly developed between 1991 and by 1940 it was a more or less complete theory. So the idea of that Kaluza-Klein theory was to unify electromagnetism and gravity. And the way they did it, they considered the 5-dimensional theory of gravity, and then compactified the 5th dimension into a circle. So for geometers, that you consider the circle bundle over the space-time. And the circle is U1, which is also the gauge group of electromagnetism. That's not a coincidence. And so for the generalized theory, the symmetric string theory, they consider 10-dimensional space-time, where the compact part is precisely dimension 6. At that time, they didn't have any idea. So this is a paper which talks about this. Again, second source in 75, I think. Yeah, so at that time, of course, they didn't have any idea what this compact set, compact manifold is. And now it took like 10-20 more years for Strominger and Witten to realize that a good candidate for that compact set compact manifold is the Calabi-Yau manifold, and the idea of flux compactification properly developed, but it was always there. And then, so now that the supersymmetry is kind of popular, again, Sartre and these three people developed the supersymmetric young males in dimension 10, and followed by a study of supersymmetric young males in dimension less than 10. They showed that you need dimension 2, 4, 6, 8, and 10 to talk about supersymmetry. And then NAM, the same NAM for of NAM transform. So he wrote a paper called Supersymmetries and Their Representation, where he explicitly showed that dimension 10 is the highest dimension for supersymmetry representations. This is a type of this should be supersymmetry. For supersymmetry representations to exist, and for supergravity, it can only go up to dimension 11. And so, of course, and now the study of supergravity in dimension 11 started. This was the paper by Kramer, and he wrote another paper called SO8 supergravity. And then we wrote this paper called a realistic Kaluza-Klein theory. Where again, they all talked about dimension 11 supergravity. And these are the three papers that motivated Oregon, Gibson, Fairlie, and Nuyts, the first three in Durham, so very close to home, yeah, to investigate young males instantons where the dimension is greater than 4. And so that was 1983. So you can see the first, the last three papers, 78, 79, 81, and then immediately in 83, they wrote this paper. And so if you recall, that's your instanton equation. And there are two things happening there. First of all, that plus minus 1 times half, and another is this epsilon mu nu alpha. So a very obvious way to generalize it for any dimension d would be this plus minus 1, put it here as lambda. And instead of this tensor epsilon mu nu alpha beta, you consider a tensor T mu nu alpha beta. T mu nu alpha beta is totally antisymmetric and should be related to a structure constant, should be related to structure constants of some subgroup of SO8, which this works. And so they refer to this equation as the secular equation. And the object is pretty clear. It's to investigate the possible choices of this lambda and these tensors, so that these equations, you can clearly tell they will give you a set of equations. To have these equations to be not over-determined, you can actually solve them, and the solution should be non-trivial. So they look from dimension 5, 6, 7, and 8. They stopped at 8. So for dimension 8, they of course tried all the maximal subgroups of SO8, and turned out the most important case was when that subgroup is spin 7. And the value of lambda also was calculated to be -1 and 3. So it turned out the eigenvalue -1 produced a set of 7 equations, where the eigenvalue 3 produced a set of 21 equations. So clearly, now you understand when people talk about high dimensional why they always work with this -1 eigenvalue. As I've been told, that it's not that you cannot find solutions with the -3 eigenvalue, but not always. May in some particular cases. Right, and considering how we get spin 7, and you have the G2 in there, which and that's the automorphism group of octonions, and the octonion structure is pretty obvious with the groups like G2 and spin 7, and so this tensor T mu nu alpha beta choice for that was just a very best and obvious choice to consider the octonionic structure constants. So that way octonions multiply. So for dimension 7, again G2, considering the maximal subgroup to be G2, maximal subgroup of SO7, that's the best choice because since the octonion structure are invariant under G2, you can just delete the 8th coordinate and of your instanton equation, and you'll precisely get your 7-dimensional instanton equation. And they also very briefly mentioned that the reason they stopped at dimension 8 was precisely the there's no division algebras above dimension 8, which I want to explore more in future to write it as a theorem or something. But the stage was set to move forward, and let's actually discover these instantons. Well, not me. People already did that. So now I'm going to talk about instantons in dimension 8, in particular on R8, which was done by these 4 people. And so, 84, Fairlie and Nuyts submitted this paper where they calculated the solution of the instanton equation in dimension 8. And soon after, Fubini and Nicolai also submitted another paper called the octonionic instanton, where which contained similar solution, almost the same solution, but obtained via a different method. So they didn't know about the earlier work, which they actually mentioned in the paper. So we'll start with the gauge group spin 7, as we mentioned, the best choice for us, and the structure constant CMNPQ, which I did as T mu nu alpha beta. So here I wrote it like this, CMNPQ, and they are the octonionic structure constant, which are defined this way. So actually, CMNP is the octonionic structure constant, and you can cook up the CMNPQ from that using this condition. So this thing is just a hot star of the 3 form with these coefficients, and this is how the 8th coordinate is done. So yeah, I'll talk about it later. And so you have the 28-dimensional SO8, Lie algebra of SO8, and you can project it to the 21-dimensional subset spin 7 by this projection formula. And then if you have the gamma matrices, so they are actually conical product of Pauli matrices. You have 8 gamma matrices, and then you can do this commutator relation to get these gamma PQ, which will turn out to be a generator of SO8. And then using this projection formula, you can get a generator for spin 7. And so they considered this unjust for the instant. So AM is your instanton. You have this generator, and then you have this function FP, which is a del P effect. And so this is the instanton equation. You can clearly see the octonionic structure constants appearing here, and they calculated the best choice. The choice for lambda should be half. Should be 1 actually. Lambda equals 1. Half was always there. And then you can calculate. So you have the unjust for AM. You can calculate the corresponding curvature using the formula. FMN equals del M AN minus del N AM plus the commutator of AM AN. And when you do that with this AM, and you get the curvature, then you plug it in there, plug those values in there, and that will give you, and then solve, and that will give you this expression for AM, which is your instanton solution. And I'm going to refer to this as FNFN instanton for Fairlie and Nuyts Fubini equation. So that's the spin 7 invariant instanton on RA developed by these four people. And then it actually took almost a decade for Güraydin and Nicolai to do the same thing for dimension 7. And they, of course, considered the gauge group to be G2. And exactly the same way they considered the generators of spin 7 and then projected it to G2 by this projection formula. And so that's the generator of G2. And then you have the structure constant C, M, and PQ. And exactly similar ansatz, and that's the instanton equation. Again, lambda equals 1. And they calculated the curvature from this ansatz for the connection and then plugged it in there, and this is the solution they got. And so that's the 7-dimensional instanton on R7, which we'll refer to as a Güraydin-Nicolai instant. And it's not surprising, it should not be surprised to you that this instanton should have using supersymmetric Mills theory and supergravity. So in 1991, Fairlie and Strominger wrote this paper, Octonionic superstring solitons. They wrote down a set of 3 equations, and one of them was this equation. And so they extended the instanton to heterotic soliton. And so that soliton solution actually described a string in 10-dimensional spacetime. And so when Güraydin Nicolai wrote their paper on where they calculated the instanton, they did that study themselves. They themselves extended the instanton to a heterotic string soliton in their paper. So that's the historical development of the 2 instantons that I'm very passionate about. And somehow all my work and the work of my predecessor, Joe Driscoll, was are done with these 2 examples in mind. Somehow these 2 examples are the most fruitful examples of our work, because we can use our work to get a lot more information about these 2 instantons, and let's see how. So now I'm gonna suddenly now it will feel like a completely different talk, because suddenly I'll start talking about some very weird differential geometry, and you are like, why is he talking about that? Well, for the people who haven't heard my talk before. So suddenly I'll start talking about this G2 idea of a G2 and spin 7 manifold. So I'll start with this Riemannian 7 manifold. Well, at least you can see the dimension 7 appearing. You may have some idea that this should relate to my the stuff that I talked about before somehow. So I'll consider 3 form, which in local orthonormal basis you can write it like this. So here E127 means E1 with E2 with E7, right? And this phi, you can generally write it as phi equals C ijk E ijk, right? So you can clearly see C127 is 1, whereas C126 should be 0. And there's a reason for me writing ijk, that those are the precisely this octonionic structure constant that I talked about before. And we'll call this phi the G2 structure. Now, if this phi turns out, this 3 from phi turns out to be, you have d phi equals d star phi equals 0, then we'll call this G2 structure a torsion-free G2 structure, and then my manifold is actually a G2 manifold. But sometimes you may not have integrability of your G2 structure. You may very well have d phi equals tau 0 psi for some non-zero subgroups. And clearly see it cannot be closed. So your G2 structure is not integrable, and then we'll call that manifold nearly G2 manifold. And this nearly is actually pretty big relaxation. So, but at least it's Einstein. I'm happy with that. Now this now I'll consider a Riemannian 8 manifold. I'll consider a 4 form which is written like this. And again, yeah.
Do you don't mind what an Einstein manifold is?
So it's a bit weaker than the Ricci curvature being 0. The Ricci curvature is actually some constant time the metric. So now if you have this 4 form again, you can write this 4 form capital phi as px. I'm using E. So E0 is phi plus star phi. And again, if you remember the way I defined the octonionic structure constant C capital M and PQ, this was precisely how I did there. So that's the 4 form, and then I'll call that this spin 7 structure, and it will be a spin 7 manifold if it's this structure is integrable. So nabla phi should be 0. It's torsion free. So now we know what a G2 and spin 7 manifold are. Let's look at this thing called asymptotically conical spin 7 manifold. So I'll start with a nearly G2 manifold. Right? And then I'll consider a cone over it. And turns out I can write down a torsion-free spin 7 structure defined by this. Well, the reason it will be torsion-free precisely because I started with the nearly G2 manifold. You can show that for a particular value of tau 0, if you got typical one is to consider is 2 4. So if you have d phi equals 4 psi, and you can prove that that implies this phi c equals 0. Nabla phi c equals 0, or the same condition is d phi c equals 0 actually as well. So nabla phi is 0 actually implies d phi equals 0. And then you can show that this spin 7 structure is actually it's torsion free. To call this sigma the nearly G2 7 manifold the link of the cone, and you'll get a metric, a conical metric. But the problem is this cone is not complete, which means you need to start with a complete manifold which geometry is very similar to this cone. And what do I mean by that? So I'll start with a non-compact spin 7 manifold. I'll call it asymptotically conical with rate nu. So this is the important part, the rate. Rate nu. If you have a compact set and a compact connected nearly G2 manifold, where you have this diffeomorphism between the cone and the manifold with the compact set removed, which satisfies this asymptotic relation involving the spin 7 structures of those two. So diagrammatically, you can think of that's your cone. Now you find a manifold is complete. You remove a compact set from it, and then the upper part, they are diffeomorphic. So that's your asymptotically conical spin 7 manifold. Now I will give you a bit of hint because you are like, this is completely unrelated to what he was talking about. If you start with the 7 sphere S7 and you consider the cone over S7, that's precisely R8 minus a point. So this compact set you removed, you can that's a point. Now you add that point to R7 minus 0 and you get the whole, sorry, R8 minus 0 and you get your whole R8. So R8 is an asymptotically conical spin 7 manifold where your link is S7. So I can see a framework emerging. This theory of asymptotically conical manifolds, at least for the manifold part, the R8 surely fits into this. It's non-compact. The asymptotically conical manifolds are non-compact. So do analysis, you need to talk about Sobolev norms and stuff like that. How do you do this for this non-compact thing? Remember the important, which I said it's important, the rate. You introduce the idea of rate in the Sobolev norm using this. So if you now think about your usual Sobolev norm on a compact manifold, these rows are precisely what's different from the usual ones. And what's this row? This row is this function where you consider it to be 1 on that compact part of your manifold. For high enough, you consider it to be R. And for the middle part, you somehow interpolate it. R is your radial. In a decreasing manner, of course. So going back, that's your Sobolev norm over a vector bundle. So you have considered a vector bundle where you had the Levi-Civita connection and you defined all these the usual way. And so you have the Sobolev space where this you have this mu in it. And so we'll call this Sobolev space the weighted Sobolev. So the idea to introduce weight is, I hope, pretty clear. It's it is in the definition of that asymptotically conical manifolds, and also asymptotically conical manifolds are not compact. So the usual ideas of Sobolev norm doesn't work. The convergence problem. So now we consider two bundles. One particular bundle where I consider this vector bundle, and I use this notation. If it's in W2K with rate mu, then I'll use this notation. Just some shorthand. So now I have the asymptotically conical spin 7 manifold. I want to construct I want to look for asymptotically conical spin 7 instantons. So the manifold has convergence property. It at infinity, you have that link, and I want to have my instanton the similar similar asymptotic nature. So I already talked about the instanton equation, but after I discussed the relation between the structure constants, ultimately they're the same. So using those 3 form phi and 4 form psi, very coordinate free notation, I can write the G2 and spin 7 instanton by this. And as I showed you the relation between, I showed you the 4-dimensional instanton equation, star FA equals plus minus FA. Well, FA, the curvature is 2 form. If you get hot star in dimension 4, you will again get 2 form. It makes sense there. Here, for the G2 instanton case, it's dimension 7. So if you weight your curvature with this 3 form pi, you will get a 5 form. And then in dimension 7, the hot star is again 2 form. So again, that equation makes sense. And for this, it's dimension 8, whereas this is 4 form. Again, dimensionally it makes sense. So how can we talk about this asymptotically conical instanton? So there are some, as I said, I want to have that asymptotic nature to be reflected in the connection. So I want it to be reflected in the bundle as well. That's where this asymptotically framed condition comes from. If you have the bundle Q over your link sigma, that's the 7-dimensional piece, and then you consider your a bundle over your 8-dimensional asymptotically conical manifold, and they should have this property. Remember, H was precisely that diffumer, and by the projection from cone to the link. And I'll call a connection on my bundle P over my 8 manifold an asymptotically conical connection with rate nu, not the same rate, mind you. If again you have the very similar asymptotic nature, asymptotic condition, and then you consider all the rates and you take the amount and call it the fastest rate of convergence for the connection. So now if I consider an instanton, then you can understand so instead of connection, I think about an instanton. It will have a fastest rate of convergence, which will converge to a lower dimensional instanton on the link.
Fastest rate of convergence is just for the instantons, right? Not just for connections in general.
No, for this, I'm not talking about instanton. This is for connection in general. If you have this asymptotic condition for any connection, see, for this, I don't need instantons at all.
But in a minute, you will.
In a minute, I'll talk about instanton. So for this setup, was
Choose it to be like constant outside a compact region. In this case, sorry, maybe I'm stop there. Why is there a? Okay, carry on. I'll ask you more later.
Okay. Okay, so I can now talk about the moduli space, which means I'll consider the gauge group, which will have this similar asymptotic nature. So it will convert to the identity at infinity. And then I can talk about moduli space of spin 7 instantons asymptotic to an instanton in the lower, on the link with rate nu, if it's a spin 7 instanton, which I defined before, and satisfies this asymptotic relation with a sigma, which is an instanton on the link. And then I'll quotient it by this gauge group I defined just now. So I want to look for, I want to study the moduli space. So best way to start is look at the deformation of these instantons. So again, the usual setup, I'll start with a nearly G2 manifold. I'll consider principal bundle over it. And then I have the asymptotically conical spin 7 manifold with the link being this sigma, and I'll consider asymptotically framed bundle over it. Now I'll consider two Dirac operators. One, twisted Dirac operator. One on my link. Okay, and for the example I talked about, the asymptotically conical spin 7 manifold is R8, and the link there is precisely S7. So for now, if you want to just think about this FNFN instanton framework, you can just think about your X to be R8 and your sigma to be S7. It will give you sufficient motivation. And then I consider two Dirac operators. So look at this negative sign. The negative sign comes from the dimension being 8. So the Hodge star will actually split your spinner bundle into two parts. The positive and the negative, and so if you restrict your Dirac operators on the respective spinner bundles, then you get the positive Dirac operator and the negative Dirac operator. And of course, for odd dimensions, your Dirac operator is self-adjoint, but this for the even dimension, it will not, and that's a whole different problem, which which requires a lot of index theory to deal with. So that's my Dirac operator, and there are some points, some critical rates. So if you add I over to it, and that turns out to be an eigenvalue of this Dirac operator, this one, on the link, then what will happen? The kernel will blow up, and this operator will fail to be a Fredholm operator. So I'm talking about the 8-dimensional Dirac operator. If this thing turns out to be an eigenvalue of the 7-dimensional Dirac operator, then the 8-dimensional Dirac operator will fail to be a Fredholm operator. This follows from this relation between I didn't write it down for obvious reasons, between the relation between the Dirac operator on the cone and on the link, and then this critical rate doesn't care about whether it's the Dirac operator on the cone or Dirac operator on the asymptotically conical manifold. And so this critical rate, it makes the index jump. You figure out where that for which eigenvalue you have this critical rate, and then the index will jump, index of the Dirac operator will jump exactly by the dimension of that eigenspace. And so let me define these two spaces. One I'll call the deformation space, which is precisely the kernel of my negative Dirac operator, and then the obstruction space, which is the co-kernel. But it's very much rate dependent, so that's my definition of the obstruction space, the complement.
Are you going to say what these tell you about the instanton itself?
That's my theorem, right?
Yes.
Of course, I'll tell you. So I'll start with an asymptotically conical spin 7 instanton, asymptotic to the nearly G2 instanton on A7 on my sigma. So I'll that instanton to be A sigma. Then, as long as I take my rates not to be the critical rate, I know the kernel blows up, my operator is very more, I can always find. Look at this map, the Güraydin map. I can find a neighborhood of 0 in my obstruction deformation space, such that this Güraydin map from the obstruction space with the origin going to the origin, I'll consider this map, and then on an open neighborhood 0 of the image of 0, that neighborhood will be homeomorphic to a neighborhood of my connection A, or rather instanton A in my modular space. Now this, I mean, just by looking at it, this theorem is not very surprising. It's pretty generic deformation theorem, except for this being the non-compact case. I needed this condition on the rate, which you will not see if you look at the deformation of 4-dimensional instantons on a compact. And of course, the virtual dimension of the modular space will precisely be the index of your data operator. So that's the dimension of the kernel minus the dimension of the co-kernel, right?
Why virtual? Why not just dimension?
Right, that comes now. So I don't know whether the obstruction space is 0 or not. And so if it's 0, then my modular space will be a smooth manifold, and I can actually talk about actual dimensions rather than virtual dimensions. So as I promised, I'll come back to my
So you said it was homeomorphic to something. What was it homeomorphic? Isn't it homeomorphic to a manifold?
locally, but
Oh yeah, but I still don't really see why you can't call that a dimension.
It's homeomorphic to the
never
zero set of a smooth map. But you don't know it's a regular.
Oh, you don't know
map.
it's regular. Okay.
Yeah. So going back to my FNFN spin 7 instanton, I want to use this setup. So S7, cone over S7, at a point you get R8. And fortunately for S7, it's a homogeneous near Legit manifold. It's in my setup perfectly. The homogeneous is a bonus because then all the analysis is just. So I'll consider S7 to be this homogeneous manifold spin 7 quotient Z2. And then I have this canonical bundle over 7 and the canonical connection A sigma. So I'll start with an ansatz A to be A sigma plus some function FR times AR. And so kind of similar, using similar techniques as FNFN themselves, I calculate what this FR should be, and that's my value of FR. And I talked about this critical rate. It's pretty clear from that the critical rate is not critical rate. The fastest rate of convergence. It's pretty clear that for this instanton, it's 2. How do I know this is the same instanton FNFN? Well, it's spin 7 invariant instanton on R8, and it's unique. A unique spin 7 invariant instanton. Now I have that theorem. I can easily, not easily, it took me 1 whole year to calculate the dimension of the modular space. I know that the dimension will jump when I have a critical rate, and critical rate plus 5/2 is the index of the Dirac operator on S7. So calculate the eigenvalues of the Dirac operator. At least I have rate -2. So if you add 3/2 to -2 and 0, then you get a range of half and 5/2, and you find all the eigenvalues of your Dirac operator on S7 in that range, and then you see how many of them are actually you add 3/2 and you subtract 3/2 and you get in that range. You stay in that range, and turns out there's only one eigenvalue, 3/2, which you can get by -1 plus 3/2, and it will stay in that range. So that's your critical rate. At that point, when you move your mu from -2 to 0, that's your range. And when you will reach -1, Finally, your dimension of the modular space will jump 8 dimensions because that eigenvalue, the eigenspace is 8 dimensions. It comes from the spin representation of space. So that's the dimension jump. How did I come up with this one? Well, that's the index calculus. I need to calculate the index of my negative Dirac operator on R8. So again, R8 is non-compact. How do I use index theorem? Consider the usual Atiyah-Singer index theorem, which is for compact manifolds. Well, there's an alternative version for manifolds with boundaries. Atiyah-Paturi-Singer. It's called the Atiyah-Paturi-Singer index theorem. And then I proved that if you consider a disk in that compact manifold, then they will have the same index. So you can always consider the non-compact manifold as a compact manifold with boundary at the boundaries at infinity. I prove that if you move it nearby, the index won't change. And then I would use the Atiyah-Paturi-Singer, and so other than the integral of curvature term, which you have seen the usual index, you have an additional eta invariant, which kind of studies the distribution of the eigenvalues because the eigenvalues are not symmetric because of this twisting done by the bundle. I have the information about the modular space of FNFN instantons. Voila. And I can do something better. It's still not completely done yet. So if I consider any asymptotically conical spin 7 instanton on R8, asymptotic to this link, then if it satisfies this condition where this C is yet to be determined, then either this instanton is obstructed, which means the modular space is not smooth, or it will be unique, and which means the FNFN instanton will turn out to be the unique asymptotically conical spin 7 instanton in that case. Now, the G2 case was done by my predecessor Joe Driscoll, and that's the result they got. So the dimension jump was 7 in that case, and exactly the similar uniqueness result, either obstructed or unique. They didn't have the condition on the integral of curvature term because, of course, the Dirac operator is self-adjoint for this case, and also he didn't need to do the index calculation as well. Dirac operator had index 0. So I included a lot of references. They are actually useful, because I referred to them in the text, the historical development of the subject. What's next? The next is to actually prove that the Güraydin Nicolai and FNFN instantons are actually unobstructed, thus establishing the modular space to be a smooth manifold, and concretely saying, well, it's the dimension of the modular space, and thus establishing the uniqueness of these instantons as well. Another project involves doing what was done for the tooped anjas, the idea of multi-instanton, and there's an idea to extend it to dimension 7 and 8, and extend it to any manifold. That's it. Maybe we should take the question outside.
Yeah, probably. I'll just say, I think the lieutenant's coming in, but let's all thank Tat again, and certainly track him down if you want to ask any further questions.